Lateral stability involves the study of moments about the longitudinal axis. If the aircraft is displaced away from wings level, the inclination of the lift vector will generate a side force, and the aircraft will start to move sideways through the air. This is known as side slip. From our study of directional stability, it is obvious that a side slip will generate a yawing moment. If we freeze the animation during the side slip, we can see that a side slip angle exists, and the resultant fin force will generate a yawing moment towards the direction from which the airflow is coming, and the aircraft will weathercock into the wind. We are seeing a sample of the interaction between lateral stability and directional stability, which will be fully explained at the end of this lesson. For the study of lateral stability, we will concentrate on the rolling moments generated by a side slip. The type of lateral stability is determined by the direction of the rolling moment generated by the side slip. If the side slip generates an unfavourable rolling moment, the aircraft will roll further away from wings level. This is unstable due to side slip. If the side slip generates no rolling moments, the aircraft will neither roll further away from nor back towards wings level. This is neutral. If the side slip generates a favourable rolling moment, the aircraft will roll back towards wings level. This is stable due to side slip. The degree of lateral stability an aircraft has is the net result of the contribution of its component parts. First, we will look at the contribution of the wing. As the aircraft side slips, the relative airflow is no longer parallel to the longitudinal axis, and the forward speed vector and the side slip vector give a resultant relative airflow from the side. It will be easier to see what is happening if a two-dimensional view is used. As the aircraft side slips, the relative airflow is from the side, which we can replace with a view of an airflow stream. We can see that the airflow path is partly over the top and partly beneath the fuselage. This airflow is around the fuselage where the wing is attached. First, we'll look at a wing mounted on the bottom of the fuselage. The wing into wind has a decreased effective angle of attack and less lift, whereas the wing out of the wind has an increased angle of attack and more lift. The difference in lift on each half of the wing will generate a rolling moment that rolls the aircraft further away from wings level. The aircraft has negative lateral static stability. The designers can reduce the unstable contribution of a low-mounted wing by fitting the wing on the fuselage at an angle. This is called dihedral. The upward inclination of the wing from the horizontal. Let's see how dihedral reduces the unstable contribution of a low-mounted wing. It is clear that dihedral removes the wing from the influence of the airflow around the bottom of the wing-fuselage junction, and the airflow over the top gives more lift on the wing into wind and less lift on the wing out of the wind, which generates a rolling moment back towards wings level. Dihedral gives an aircraft with a low-mounted wing positive lateral static stability. We will now take a look at the high-mounted wing. The airflow over the top of the fuselage wing junction gives more lift on the wing into wind and less lift on the wing out of wind. which generates a rolling moment back towards wings level. An aircraft with a high-mounted wing has positive lateral static stability merely because of the wing position on the fuselage. Because a high-mounted wing gives the same positive contribution to lateral stability as does dihedral, a high-mounted wing is known as a dihedral effect. A designer may decide on a high wing configuration because a low fuselage position with the aircraft on the ground is desirable for ease of loading. Potentially, the dihedral effect of the high wing may give too much lateral stability. If so, the designer can reduce the stable contribution of a high wing by fitting the wing at a downwards angle. This is called anhedral, the downward inclination of the wing from the horizontal. Most jet transport aircraft have a swept wing to increase the efficiency of high-speed flight. In a right side slip, the wing into the wind has less effective sweep angle, and the wing out of the wind has more effective sweep angle. This gives more lift on the right wing and less lift on the left wing, which generates a stabilizing left rolling moment. The swept wing provides a stable contribution to lateral stability, so is also classified as a dihedral effect. If an aircraft has a high-mounted wing that is also swept, it will have two dihedral effects, and may have too much lateral stability. If this is the case, the wing will require anhedral to ensure the proper amount of lateral stability. The fin has already been identified as the aerofoil that provides directional stability. But in a side slip, the aerodynamic force on the fin acts above the CG, which generates a small stabilizing moment. The fin, therefore, is also a dihedral effect, but a small one. The contribution of a ventral fin is very small indeed. As you can see, the aerodynamic force is in the same direction, but is acting below the CG, and is destabilizing. For all practical purposes, any contribution of the ventral fin to lateral stability is insignificant. The illustration shows the low pressure area on the top of the wing. Each half of the wing generates a share of the lift, and each component of lift will act at a certain distance from the CG. Any change in lift in a side slip will act through a given arm length to generate a rolling moment. When the flaps are down, the inboard portion of the wing generates a larger percentage of the lift, and each component of lift will be located further inboard. With the flaps down, any change in lift in a side slip will act through a shorter arm and generate a smaller rolling moment. Hence, with flaps down, lateral stability is reduced. As has become increasingly obvious, in a side slip, the lateral and directional response of an aircraft will be coupled. Side slip will simultaneously produce a rolling and a yawing moment. The type of lateral dynamic stability an aircraft will exhibit is determined by which type of static stability is dominant, directional or lateral. If directional static stability is dominant, the aircraft will suffer from spiral instability. If lateral static stability is dominant, the aircraft will suffer from Dutch roll, a combination of rolling and yawing. Because jet transport aircraft have a swept wing, they have a tendency to Dutch roll, and are fitted with a device called a yaw damper to prevent it.
This lesson will cover the basic flying controls, their location on the aircraft, their operation and primary effects, and the various methods available to designers for making control of the aircraft easier and safer for the pilots, and ultimately, of course, safer and more comfortable for the passengers. Variations on the basic configurations will be covered in a subsequent lesson. The basic method of changing the attitude of an aircraft, that is, its position relative to the horizon, is by temporarily changing the camber of the aerofoil of the wing, tailplane or fin, which will alter the lift it produces. The diagram shows the change in lift with changes in control surface position. The overall effect of a control movement will also depend on speed. An aircraft needs to be controllable about each of its three axes, which pass through the centre of gravity, or CG, which is conventionally portrayed by a circle with alternate black and white quarters. Basic controls will consist of flap-type sections incorporated into the trailing edges of the main flying surfaces, and positioned at the extremities furthest from the CG to give the greatest control movement. One axis runs vertically through the centre of gravity. This is the normal axis, movement about which is controlled by the rudder, the vertical control surface attached to the fin. The movement around the normal axis is called yaw and can be termed directional control. It is worth noting, however, that the rudder is not used to change direction by yawing the aircraft, but rather for preventing yaw, both in normal and asymmetric flight. This will be covered in more detail in a later lesson. The lateral axis passes through the CG running parallel to a line passing through the wingtips. And movement around this axis is called pitch. The control surfaces are the elevators, which move up and down together to give longitudinal control and are mounted on the trailing edge of the tailplane. The third axis is the longitudinal axis, which runs from nose to tail through the CG. Movement around this axis is called roll and is provided by the ailerons, which are mounted at or near the wingtips. They move in opposition. The downgoing aileron increases the lift on that wing, and the upgoing one decreases lift on the other, giving lateral control. These are the conventional three-axis basic control surfaces. In the following lesson, we shall look at variations on the basic types of control surfaces. It has been stated that aircraft are fitted with flap-type controls, and that flap-type controls generate the required moment about the CG by changing the camber of the aerofoil. There are two other types of control surface that do not change the camber of the aerofoil. The all-moving slab tailplane is sometimes used instead of an elevator for pitch control, when an elevator would not be powerful enough. The pilot changes the angle of incidence of the whole tailplane to generate the required pitching moment. The tailplane pivots around a hinge when the pilot moves the control column fore and aft. Backward movement of the control column decreases the incidence of the tailplane to generate an aircraft nose-up pitching moment. Forward movement of the control column increases the incidence of the tailplane to generate an aircraft nose-down pitching moment. Spoiler surfaces can be used to help the ailerons generate the required rolling moment. Spoilers literally spoil or disrupt the airflow over the wing, which decreases lift and increases drag. Spoiler surfaces will be explained in detail later. The force the pilot must apply to move the control surfaces into the airflow or hold the required angle of deflection must not be too high. When the pilot moves a control surface into the airflow resists. An aerodynamic force will try to rotate the surface around the hinge in the direction in which the force is acting. The product of the aerodynamic force and the distance from the hinge line to the centre of pressure of the control is called the hinge moment. It is the hinge moment the pilot must oppose to make and hold the required control deflection. The pilot refers to the hinge moment as stick force or feel. If the control deflection is increased, so is the hinge moment. As the IAS is increased, the hinge moment is increased for the same control deflection. Larger aircraft require control surfaces of larger area, and this will also increase the hinge moment. So the greater the displacement, IAS or surface area, the greater the hinge moment. For large and fast aircraft, therefore, the hinge moment could become so high that the pilot would have great difficulty in making and holding the required control input. Therefore, the pilot may require assistance to move the controls. This is done either by using some form of aerodynamic balance or power flying controls. The first type of aerodynamic balance we will consider is the inset hinge. We have seen that the hinge moment is a product of the aerodynamic force, F, and the distance of the centre of pressure from the hinge line, D. During manufacture, the control surface hinge is positioned aft of the control surface leading edge. This reduces distance, D, and thus reduces the hinge moment. Most aircraft with manual controls have inset hinges on the ailerons, elevator, and rudder. The designer must make sure that the control surface centre of pressure can never move forward of the hinge line. This would cause the control surface to self-select or increase in deflection. This is known as overbalance and can never be allowed to happen. A typical inset hinge looks like this. The area of the control surface forward of the hinge line is shielded to prevent it protruding into the airflow. The second type of aerodynamic balance we will consider is the horn balance. A small area of the control surface is positioned forward of the hinge line at the outboard end. The horn generates a small aerodynamic force that opposes and therefore decreases the hinge moment. The area of the horn balance is carefully calculated so that overbalance is prevented. The horn balance is used on the rudder and elevator, but not the ailerons. The third type of aerodynamic balance we will consider is the internal balance, which uses the pressure difference between the upper and lower surfaces of the aerofoil to reduce the hinge moment. The internal balance consists of a seal between the leading edge of the control surface and the trailing edge of the aerofoil. The seal is in the form of metal panels with appropriate hinges to allow movement. The internal balance is very effective and is still used on some modern jet transport aircraft and business jets, even those with powered flying controls, as they relieve the stresses on the structure where the hydraulic actuators are attached. The preceding three types of aerodynamic balance reduce the hinge moment by adjusting the aerodynamic force, or the arm, forward of the hinge line. We will now consider devices that reduce the hinge moment by generating forces aft of the hinge line. These devices are collectively known as tabs, a small aerofoil mounted on the trailing edge of the main control surface. The following illustrations are schematic. They just show the operating principle of the device. In reality, the mechanisms will be inside the structure. The first tab we will consider is the balance tab. The pilot input is connected to the control surface so that when the pilot moves the cockpit control, he or she is directly moving the control surface. There is a link between the fixed structure and the balance tab, such that when the pilot moves the control surface, the balance tab moves in the opposite direction. Please note, it is movement of the control surface that moves the balance tab. Therefore, if for some reason the main control surface can't be moved, the balance tab can't move. It is the aerodynamic force on the balance tab acting in the opposite direction to the one on the control surface which reduces the hinge moment. Because the balance tab moves in the opposite direction to the control surface, the effectiveness of the control is reduced. This is because the opposite motion of the balance tab reduces the change in camber commanded by the pilot. In practice, the designer will compensate for this. To summarize, the balance tab reduces the hinge moment, stick force and feel. The pilot moves the control surface moves the balance tab. The balance tab moves in the opposite direction to the control surface, giving a reduction in control effectiveness. The second type of tab we will consider is the anti-balance tab. The pilot input is connected to the control surface so that when the pilot moves the cockpit control, he or she is directly moving the control surface. There is a link between the fixed structure and the anti-balance tab, but this time when the pilot moves the control surface, the anti-balance tab moves in the same direction. Please note, the anti-balance tab is the only tab that moves in the same direction as the control surface. It is the aerodynamic force on the anti-balance tab acting in the same direction as the one on the control surface that increases the hinge moment, stick force and feel. Because the anti-balance tab moves in the same direction to the control surface, the effectiveness of the control is increased. This is because the motion of the tab now increases the change in camber commanded by the pilot. The anti-balance tab is fitted to aircraft that otherwise would suffer from either a lack of control effectiveness or stick forces that are too low. To summarize, the anti-balance tab increases the hinge moment, stick force and feel. The pilot still moves the control surface directly, and it is the control surface that once again moves the anti-balance tab. The anti-balance tab moves in the same direction as the control surface, giving an increase in control effectiveness. The third type of tab we will consider is the servo tab. The servo tab is very different from the preceding two tabs. The horn is merely pivoted on the control surface and is free to rotate. The pilot input directly moves the horn. But this time the link is connected from the horn to the servo tab. Thus, when the pilot makes a control input, it is the servo tab that is being moved, without any mechanical input to the control surface. It is only when the aircraft has sufficient IAS that the aerodynamic force generated by the servo tab can move the control surface. The aerodynamic force on the servo tab moves the control surface in the opposite direction. Because the pilot is only moving the servo tab into the airflow, the hinge moment, stick force and feel are reduced. If the aircraft has powered flying controls and a hydraulic failure occurs, a servo tab can be used for what is called manual reversion. That is, the pilot will still be able to move the servo tab and hence the control surface even at high IAS and maintain control of the aeroplane. Because the servo tab moves in the opposite direction to the control surface, the effectiveness of the control is reduced. The servo tab has other disadvantages. The first disadvantage is that when flying at lower IAS, the smaller aerodynamic force from the servo tab will give reduced control surface movement, when in fact the pilot requires an increased control surface movement. In practice, the designer will compensate for this. The second and more significant disadvantage of the servo tab concerns the fitment of control locks. If your aircraft is fitted with servo tabs, you must physically check that the control locks have been removed before flight. Because the pilot only moves the servo tab, the full and free control movement check in the cockpit will not alert you to the fact that the control locks are still engaged, and you will not be able to control the aircraft. The control locks of some aircraft can be engaged and disengaged from the cockpit, and when engaged will prevent access to a vital item, such as engine start, in order to minimize accidentally trying to take off with the control locks engaged. To summarize, the pilot can move the servo tab only. The servo tab moves in the opposite direction to the control surface and therefore reduces control effectiveness. The servo tab reduces the hinge moment, the stick force and control feel. The servo tab has reduced effectiveness at low IAS, and you must physically check that control locks have been removed before flight. Because the pilot is only moving the servo tab and not the control surface, the servo tab can be used for manual reversion in the event of hydraulic failure to powered flying controls. This will be discussed in detail in the next segment. To overcome the reduced effectiveness of the servo tab at low IAS, a spring tab can be fitted, the fourth type of tab. The horn is merely pivoted on the control surface and is free to rotate. The pilot input directly moves the horn. The link is connected from the horn to the spring tab. When the pilot makes a control input, the spring tab is being moved directly by the pilot without any direct input to the control surface. So far, exactly the same as the servo tab. But now you can see there is a spring fitted between the horn and the control surface, so that when the pilot makes an input at low IAS, the control surface and the spring tab move together, giving maximum effectiveness. Progressively, as the IAS increases, there is a greater aerodynamic force on the control surface that resists the attempt of the pilot to deflect it into the airflow, causing the spring to be compressed. Compression of the spring makes the spring tab move in the opposite direction to the control surface, so the hinge moment, stick force and feel is reduced. The higher the IAS, the greater the spring tab deflection and the more assistance the spring tab provides. To summarize, at low IAS, the spring tab doesn't move relative to the control surface. The pilot moves the control surface and the spring tab together for maximum effectiveness. At higher IAS, the spring tab acts as a servo tab by moving in the opposite direction to the control surface, and therefore reducing control effectiveness. At high IAS, the servo tab reduces the hinge moment, the stick force and control feel. The spring tab can also be used for manual reversion in the event of hydraulic failure to powered flying controls. This will be discussed in detail in the next lesson. You have been shown that large and/or fast aircraft have high stick forces because of the large hinge moments generated. Stick forces that are too high make an aircraft difficult for the pilot to control. If aerodynamic balance cannot provide the required assistance to the pilot, powered flying controls must be used. Powered flying controls are hydraulically operated, either using a tapping from the aircraft main hydraulic system or alternatively using completely self-contained power packs. Powered flying controls can be divided into two categories: power-assisted and fully powered. We will start by looking at power-assisted flying controls. In a power-assisted flying control system, the Power Flying Control Unit, referred to as a PFCU, provides most of the force necessary to reduce the hinge moments. The pilot normally provides only the remaining force. These first few animations merely show the sequence of the operating principle. When the pilot moves the control column, you can see that both the control surface and the servo valve are moved. Movement of the servo valve provides a path for hydraulic fluid under pressure to one side of the PFCU piston, and opens the other side to return. However, the piston cannot move because it is connected to the aircraft structure. But the PFCU body is free to move the control surface. The reason for this design arrangement is to make sure that the control surface is moved to the angle and at the rate required by the pilot. This is called follow-up. The force from the hydraulic system moves the body of the PFCU and the control surface until the input from the servo valve is cancelled by the motion of the PFCU body. A hydraulic lock now exists. In reality, as soon as the pilot starts to move the cockpit control, the PFCU immediately moves the control surface to the angle and at the rate of motion commanded. It can be seen that a small proportion of the aerodynamic force generated by moving and holding the control surface into the airflow is still felt by the pilot as stick force, so the natural feel of the controls is retained. The stick force will change in proportion with the square of the IAS, as it would in a purely manual control system. If hydraulic pressure is lost from a power-assisted flying control, the pilot would still be able to control the aircraft, but with significantly higher stick forces. Power-assisted flying controls, therefore, do not require a separate manual reversion system. If the speed or size of an aircraft dictates, a fully powered system will be fitted. As before, these first few animations merely show the sequence of the operating principle. When the control column is moved, the servo valve directs the hydraulic fluid under pressure to one side of the piston and opens the other side to return. The body of the PFCU will move the control surface until the body reaches the position of the servo valve, and then it will stop. The fluid in the PFCU is now trapped, giving a hydraulic lock that prevents any movement of the control surface by the airflow. In reality, as soon as the pilot starts to move the cockpit control, the PFCU immediately moves the control surface to the angle and at the rate of motion commanded. In the fully powered system, there is no mechanical connection between the control surface and the cockpit control. Therefore, the pilot has no stick force or feel at all and could accidentally overstress the aircraft. Previously described devices merely reduced the stick force or feel to manageable levels. There was always an aerodynamic force present at the cockpit control to give a sense to the pilot of the input made. In other words, the pilot could feel the input they had made on the cockpit controls. This feel is essential. A device must be incorporated in a fully powered flying control system to duplicate the required stick force or feel artificially. The artificial feel unit responds to changing dynamic pressure in the same way as an airspeed indicator. And because the symbol for dynamic pressure is Q, the device is also referred to as Q-feel. As before, these illustrations are schematic to show the operating principle. If hydraulic pressure to fully powered flying controls were lost, the aircraft would become uncontrollable. So some alternative means of control must be provided to guarantee safe flight. This can be done either by manual reversion or designing redundancy into the power flying control system. Manual reversion can be achieved by either servo tabs or spring tabs. In the event of hydraulic failure to the PFCU, a valve automatically opens to provide a path for the fluid across the piston. This cancels the hydraulic lock and allows movement of the control surface by either a servo tab or spring tab. Redundancy involves the use of multiple, completely independent hydraulic systems to power the flight controls. Each control surface can also be split with each segment powered by a separate hydraulic system. For modern jet transport with only 3, and more commonly 2, gas turbine engines, a ram air turbine, or RAT, is fitted to maintain adequate redundancy. In the event of an engine and/or a pump failure, the RAT can be deployed to provide a hydraulic flow to the primary flying controls only. To summarize, power flying controls must be used on large and/or fast transport aircraft that have control forces too high for the average pilot. Power-assisted controls retain some of the control's natural feel, but most of the force required is provided hydraulically. Fully powered controls use hydraulics to provide all the force needed to move the control surfaces into the airflow, but there is no direct link between the pilot's controls and control surfaces, and therefore an artificial feel system is required to give the pilot the stick force necessary to fly the aircraft safely. Control surface flutter can affect the ailerons, the elevator and the rudder. Of the three, we will consider aileron flutter, being perhaps the easiest to visualize. The movements shown are deliberately exaggerated for clarity. When an aileron is deflected downwards into the airflow, an aerodynamic force will be generated, acting upward at the hinge line. This aerodynamic force will twist the wing about its torsional axis and start to wind up the wing like a spring. Because the CG of the control surface is aft of the hinge line, and because there is always a small amount of backlash in the control system, when the wing twists, the aileron displacement will be increased slightly. The increased deflection of the aileron will give an increased twisting force to the wing. This set of actions will repeat. Eventually, the rate of wing twist will decrease and the aileron will start to catch up with the twisting wing, and then the whole process will reverse and become divergent. The result of aileron flutter is here illustrated. Clearly, this is unacceptable and must be prevented. Don't forget, this can occur with the rudder and elevator too. The pilot cannot prevent flutter. Even if you hold the cockpit controls rigid, backlash in the control run will still allow the control surfaces to flutter. Even power flying controls have some backlash. You might think that to reduce control surface flutter, the wing could be made stiffer to stop it twisting. Theoretically, yes, but no structure is absolutely rigid, and increased stiffness increases structural weight, something to be avoided. Remember, reducing flutter is not acceptable. Flutter must be prevented. The control surfaces themselves must have their mass redistributed to prevent them lagging when an input is made. This is called mass balance. To prevent flutter, the CG of the control surface is moved forward onto the hinge. You can see that the force on the hinge line still twists the aerofoil, but there is no increased control surface deflection. A weight is added in front of the hinge to move the CG of the control surface forward onto the hinge line. To minimize the size of the mass balance weight, the weight is sometimes mounted on an arm, as illustrated. When possible, the mass balance weight is mounted inside the aircraft structure to minimize drag. If possible, the presence and security of mass balance weights should be checked during the pre-flight walk-round. Control in pitch is usually achieved with an elevator or, on a few light aircraft, by an all-moving slab tailplane. This entire sequence is simplified for clarity, and we will ignore the effect of any change in IAS. Consider an aircraft in equilibrium at a steady speed with the elevator neutral. If the elevator is deflected up, the tailplane will develop an increased down force that will begin to pitch the aircraft nose up. As the aircraft begins to pitch up, static longitudinal stability will start to give an opposing nose-down pitching moment, and when the two pitching moments are equal, the aircraft will stop pitching. To hold that particular pitch angle, the elevator must remain displaced. Hence, the elevator is known as a displacement control. If we consider the CG further forward from our previous studies, static longitudinal stability will be increased, and a greater upward deflection of the elevator is required to hold the same pitch angle. This is not something that would happen in flight, but shows that, with a forward CG, a greater elevator deflection is required for a given pitch angle. For this example, to return to level flight, the elevator is returned to neutral and the static longitudinal stability will pitch the aircraft nose down. Smaller aircraft use ailerons for control in roll, but the majority of modern high-speed jet transport aircraft use a combination of ailerons and spoilers. You may consider this a strange-looking aeroplane, but the two halves of the wing and the cockpit control have been displayed this way to give as large a view as possible. Also, the aileron displacement shown in the following illustrations is emphasized for clarity and is much bigger than that required in practice. If the control wheel is moved to the left aileron moves up. This decreases the camber of the wing in the vicinity of the aileron and reduces lift. At the same time, the right aileron moves down. This increases the camber of the wing in the vicinity of the aileron and increases lift. The difference in lift on the two halves of the wing generates a rolling moment to the left, and the aircraft will start to roll to the left. If you were to hold the ailerons displaced from neutral like this, the left rolling moment would still exist and the aircraft would continue to roll to the left about the longitudinal axis. In normal flight, not something you would want to happen. Clearly then, ailerons are not a displacement control like the elevator. Ailerons are a rate control. If ailerons are displaced from neutral only slightly, the aircraft will roll slowly. The greater the aileron displacement, the greater the rate of roll. Usually, you roll the aircraft to a given bank angle to change heading, in other words, to turn. To hold a given bank angle, you must reduce the rolling moment to zero by returning the ailerons to neutral. Please bear in mind that we are presenting only the principles of flight. When you start flight training, your instructor will show you what is actually required to hold a constant bank angle, but don't worry, it's not fundamentally different. Just before you reach your desired heading, to allow for the time taken to roll the aircraft back to wings level, you turn the control wheel to the right. The left aileron moves down. This increases the camber of the wing in the vicinity of the aileron and increases lift. At the same time, the right aileron moves up. This decreases the camber of the wing in the vicinity of the aileron and decreases lift. The difference in lift on the two halves of the wing generates a rolling moment to the right, and aircraft will start to roll to the right, in this case back towards wings level. Just before you get to wings level, you neutralize the ailerons, which reduces the rolling moment to zero, and the aircraft will stop rolling. We will now look at the byproducts of rolling the aircraft about the longitudinal axis. The first consideration is our old favourite, aerodynamic damping. We will assume a constant IAS, but you should remember that aerodynamic damping is a function of TAS, not IAS. Please note the true airspeed vector. Only the downgoing wing is illustrated. The opposite will take place on the upgoing wing, but will have the same effect. The aileron has been moved up to generate a downforce. The aircraft will begin to roll. This wing is now moving downwards in addition to moving forwards. The black vector represents the downward speed of the wingtip. The blue vector represents the effective airflow and is the resultant of the TAS and the rate of roll. The angle between the TAS vector and the effective airflow vector is the change in effective angle of attack. This increase in effective angle of attack on the downgoing wing generates an up force called aerodynamic damping. aerodynamic damping reduces the rate of roll. When the aircraft stops rolling, there is no longer any aerodynamic damping. At a constant IAS, a higher altitude will require a higher TAS. The same aileron deflection will produce the same aileron force because the IAS is constant. But because the TAS is higher, the increase in effective angle of attack is smaller. This results in reduced aerodynamic damping and consequently a higher rate of roll. To achieve the same rate of roll with an aircraft of greater wingspan, the ailerons must be deflected through a greater angle. Because the wingtip is further from the CG, the wingtip has to move downwards through the air faster, increasing aerodynamic damping. The second byproduct of rolling the aircraft about the longitudinal axis is adverse aileron yaw. The objective when rolling the aeroplane is usually to turn to a different heading, as previously described and here animated. If both ailerons move through the same angle from neutral, the downgoing aileron will generate more drag than the upgoing aileron. Parasite drag is the same on both, but the downgoing aileron would generate an increase in induced drag, and the upgoing aileron would generate a decrease in induced drag. Only the downgoing aileron is illustrated. The adverse aileron yaw illustrated here is greatly exaggerated for clarity. The result of adverse aileron yaw is a yawing moment in the opposite direction to that required. If you roll the aircraft, in this case to the left, a yawing moment to the right is generated. This is both aerodynamically inefficient and physically uncomfortable for all on board. It must be pointed out, it's only during the roll, while the ailerons are displaced from neutral, that adverse aileron yaw occurs. Aircraft designers can reduce adverse aileron yaw in several ways. The first method we will look at is differential ailerons. The downgoing aileron moves through a smaller angle than the upgoing aileron. This reduces the difference in drag. Nearly all aircraft have differential ailerons. The second method of adverse aileron yaw reduction we will look at is the freeze aileron. The leading edge of the upgoing aileron projects below the wing, increasing the parasite drag. The downgoing aileron does not project into the airflow. It can be seen that freeze ailerons also reduce the difference in drag. Freeze ailerons are usually used together with differential ailerons on small and medium-sized aircraft. The third method of adverse aileron yaw reduction we will look at is aileron rudder coupling. Aileron rudder coupling is usually used on large modern aircraft. There is an interconnection between the ailerons and the rudder, such that when a roll input is made, the rudder is automatically deflected to cancel the adverse aileron yawing moment. Note, the difference in drag from the ailerons still exists. The fourth and final method of adverse aileron yaw reduction we will look at is roll spoilers. Most modern high-speed jet transport aircraft use roll spoilers to assist the ailerons with roll control. The operation of roll spoilers will be fully explained later. As you can see, the spoiler surface comes up on the side with the upgoing aileron, matching the drag on the two sides and thus reducing adverse aileron yaw to a negligible amount. You have seen that ailerons are mounted as far outboard as possible to give the longest arm from the CG. This is done to minimize aileron size and the angular displacement required for a given rolling moment. Unfortunately, this wingtip location also maximizes the ability of the ailerons to twist the wing. The downgoing aileron increases the camber of that part of the wing with the objective of generating an up force on the wingtip to roll the aircraft. But the wing twist will decrease the wing incidence and reduce the roll force. If we consider a higher IAS, the wing twist will be greater for the same aileron displacement, further reducing the rolling moment. Eventually, an IAS will be reached when the effect of the aileron is cancelled by the effect of the wing twist and the aircraft will not roll when commanded by the pilot. Higher IAS will give a larger rolling moment from the wing twist than from the ailerons, and the aircraft will roll in the opposite direction to that commanded by the pilot. This phenomenon is called high-speed aileron reversal and would limit the maximum operating speed of the aircraft. Making the wing stiffer to increase the IAS at which high-speed aileron reversal occurs is not an option because it would increase the structural weight of the aircraft. Instead, another pair of ailerons is fitted further inboard on a stiffer part of the wing. These are called inboard ailerons. At low indicated airspeeds, you can see that both the inboard and outboard ailerons operate through their full angle of displacement when commanded from the flight deck. We can see that the aeroplane is flying slowly because the trailing edge flaps are down. After takeoff, the aircraft is accelerated, and when the IAS reaches the speed at which the aircraft can fly safely with the flaps up, the flaps are retracted. As the flaps retract, a mechanism reduces the input to the outboard ailerons. So, as the trailing edge flaps retract, the outboard ailerons will move through a progressively smaller angle than the inboard ailerons. With the flaps fully retracted, the outboard ailerons no longer move, only the inboard ailerons. To complete your understanding, please note the following. The reduction in outboard aileron movement with decreasing trailing edge flap angle is referred to as locking out the outboard ailerons, as in, flap retraction locks out the outboard ailerons. Outboard ailerons can also be called low-speed ailerons. Inboard ailerons can also be called high-speed ailerons or all-speed ailerons. The outboard low-speed ailerons only work when the trailing edge flaps are down. When the trailing edge flaps are retracted, the outboard low-speed ailerons are locked out. The inboard high-speed, all-speed ailerons always work. Please review this scene several times to ensure you remember the complexities. You have previously been shown that flaps are fitted to the trailing edge of the wing, and you have now been shown that ailerons also occupy part of the wing trailing edge. The resulting reduction in flap area reduces the efficiency of the flaps. On large, modern high-speed jet transport aircraft, this reduction in flap area is a significant disadvantage, so design changes have been made to make the ailerons also work as flaps. Hence the name flaperons. When the trailing edge flaps move down, the flaperons also go down. Now the whole wing area has its camber increased, thus maximizing the effect of the flaps to increase CL max. But what about lateral control? Think of the flaperon position with the flaps down as a new neutral datum. When a roll input is made, the flaperons move up and down from this new neutral datum and still provide a change in lift on both halves of the wing for roll control. Spoilers are usually fitted to large, modern, high-speed jet transport aircraft to help the ailerons with roll control. Spoilers are movable panels on the top of the wing. They are hinged at their forward edge and activated hydraulically. When raised into the airflow, spoilers spoil or disturb the airflow, thus decreasing lift and increasing drag. Roll spoilers are activated by the control wheel and move up on the side with an upgoing aileron, proportional to aileron displacement. You can see that the roll spoilers on the side with the downgoing aileron remain flush. Even with the flaps up, the roll spoilers continue to assist the ailerons with roll control. Roll spoilers have several advantages over ailerons. Roll spoilers eliminate adverse aileron yaw. Roll spoilers do not twist the wing. Roll spoilers do not develop flutter. Roll spoilers do not take up space on the trailing edge, leaving it usable for flaps. Because spoilers work by reducing lift, their use will always result in a net loss of lift on the wing. This is not normally a significant disadvantage. When selected by the pilot, speed brakes increase drag. The use of speed brakes increases deceleration and/or gives an increase in the rate of descent without increasing the IAS. There are two common methods of mounting speed brakes: wing-mounted or rear fuselage mounted. Ideally, speed brakes should give an increase in drag without affecting lift or causing a change in pitching moment. Fuselage-mounted air brakes are best suited to do this, but are only occasionally used on civilian transport aircraft. Modern high-speed jet transport aircraft usually use the spoiler surfaces on the wing as speed brakes. There is a speed brake lever on the flight deck that, when selected to up by the pilot, extends the speed brakes symmetrically, thus increasing the drag. There are no speed restrictions for the operation of speed brakes. However, the design of the hydraulic operating system does give a blowback facility. That is, for the same selection from the flight deck, increasing IAS restricts the speed brake angle of deflection into the airflow. This prevents excessive buffeting at higher IAS. While being used as speed brakes, the spoiler surfaces will continue to assist the ailerons with roll control. To illustrate this, we will pull partial speed brakes. Now, when a roll input is made, the spoiler surfaces will move up or down about the datum of the speed brake selection. In flight, the maximum angle to which the speed brakes can deploy is restricted to prevent excessive loss of lift and excessive buffeting. But as soon as the aircraft touches down, there is a need to remove as much lift from the wing as possible so that the wheel brakes will have maximum effectiveness. In addition, there is a need to increase drag as much as possible. After touchdown, the air-ground logic system senses the aircraft is on the ground and removes the restriction on speed brake angle. When full speed brakes are demanded from the flight deck with the aircraft on the ground, the speed brakes deploy to a much larger angle than in flight. This is called lift dump. The rudder gives directional control about the normal axis. The rudder is not used to steer the aircraft like a boat. The main use of the rudder is to balance the aircraft, to maintain coordinated flight, but in addition, the rudder is used to fulfill several other particular functions. The first use of the rudder we will look at, and perhaps the most important, is to give the pilot the ability to maintain directional control in the event of an engine failure on a multi-engined aeroplane. A propeller-driven aeroplane is illustrated, but the same would be true if it was powered by gas turbines. The left engine fails and a left yawing moment is generated. Assuming the pilot makes no correction, the aircraft would yaw to the left. The yaw to the left would increase the lift on the right wing and decrease the lift on the left wing. This would make the aircraft roll to the left, and the rolling moment could not be stopped with roll control. So, if the pilot did not respond to an engine failure in a correct and timely manner, this would happen. The roll would reduce the vertical component of lift and the aircraft would spiral dive. At low altitude, this would be catastrophic. Whenever an engine failure occurs on a multi-engine aircraft, the first thing the pilot must do is stop the yaw with rudder. Asymmetric thrust will be fully covered in later lessons. The second use of the rudder we will look at is takeoff or landing with a crosswind. The landing approach is illustrated with a right crosswind. If you position the aircraft on the extended runway centerline with a right crosswind, the aircraft will drift to the left. What you should do is position the aircraft on the extended runway centerline, but fly it in a direction slightly towards that from which the crosswind is coming, in this case to the right. Please note, you are not using the rudder to do this. You are now tracking the extended runway centerline, but with the aircraft at an angle to the direction of flight. If you were to touch down in this attitude, you would damage the undercarriage. You use the rudder to align the aircraft with its direction of travel. Not too early, or the aircraft will start to drift sideways. Not too late, otherwise you will damage the undercarriage. The third use of the rudder we will look at is something we have already considered: balancing adverse aileron yaw. The fourth use of the rudder we will look at is spin recovery. Full rudder must be applied in the direction opposite to that of the rotation of the aircraft. In this case, rudder to the left. The fifth use of the rudder we will look at is opposing the propeller turning effects. There are 4 propeller turning effects which will be fully explained in a later lesson. We will consider spiral slipstream here. The propeller on the majority of aircraft rotates clockwise when viewed from the rear. Therefore, the prop wash will also rotate clockwise and approach the fin from the left. This generates a left yawing moment. The left yawing moment from the propeller slipstream is balanced by an application of right rudder from the pilot. Consider an aircraft in straight, steady flight. If the rudder is deflected to the left, the camber of the fin is changed and an aerodynamic force, here in blue, will act to the right at the fin centre of pressure. The aircraft will yaw to the left. Ignoring any rolling moment generated by the yaw, the aircraft will continue in the same direction of flight, here shown by the true airspeed vector. The airflow is now approaching from the right, changing the effective angle of attack of the fin, which generates an opposing side force acting to the left, the fin force, here in red. When the fin force equals the rudder force, the aircraft will stop yawing about the normal axis, and a steady side slip angle will exist. The aircraft is not turning, it is side slipping, in this case to the right. When the rudder is returned to neutral, the rudder force is removed. The fin force will yaw the aircraft to the right, until once again it is in straight, steady flight. You have seen that to hold a constant side slip angle, the rudder must remain displaced from neutral. Therefore, like the elevator, the rudder is a displacement control. As with all aerofoils, the fin has a critical angle of attack, the angle of attack at which it will stall. If the side slip angle is too large, the fin could stall. In this example, we are considering a large crosswind gust. Fin stall must be prevented. The designers can increase the stalling angle of the fin by sweeping the fin backwards, or by decreasing the aspect ratio of the fin by fitting a dorsal fin. The rudder on any aeroplane must be powerful enough for the worst case event. For the rudder of a large modern jet transport aircraft, the worst case event is an engine failure at low IAS. At other times, however, that much rudder power would be excessive, so large modern jet transport aircraft are fitted with a rudder ratio changer. The illustration shows a large modern jet transport aircraft at low IAS. Full rudder pedal travel has resulted in maximum rudder displacement from neutral. In this example, we assume the pilot is making a maximum rudder command from the flight deck. You can see that full rudder displacement is available up to about 160 knots indicated airspeed. Above that speed, the rudder ratio changer reduces the maximum available rudder displacement at a rate inversely proportional to IAS to maintain the required rudder authority. To complete this lesson, we will look at the secondary effects of both rolling and yawing. Pitching the aircraft does not give a secondary effect. The secondary effect of roll is yaw. Adverse aileron yaw has already been described, producing a yawing moment opposite to the direction of roll because of the difference in drag from the ailerons on each side. The yaw from the roll is increased by the change in direction of the lift vectors on the downgoing wing and the upgoing wing. Only the downgoing wing is illustrated. You can see that the lift vector acts at 90 degrees to the effective airflow, giving a forward component of lift on the downgoing wing. Thus the yawing moment from the roll is increased. When the aircraft stops rolling, the yawing moment will be absent. We have merely frozen the animation for your further consideration of the vectors and forces. The secondary effect of yaw is roll. In this example, the aircraft is yawed to the left. The right wing is accelerated and the left wing is decelerated. Therefore, the right wing will generate more lift and the left wing will generate less lift. A left yaw will give a roll to the left. A right yaw will give a roll to the right. If the rudder is deflected to the left, an aerodynamic force will be generated to the right, acting through the fin centre of pressure. Because the fin centre of pressure is located above the aircraft CG, a right rolling moment will be generated. Please remember that a moment will not necessarily give movement. You must appreciate that we are only considering the effect of displacing the rudder, not the yaw that would result. To fly an aircraft in a steady state, climb, cruise or descent, the pilot must apply the stick force necessary to hold the aircraft in the required attitude. In other words, the pilot must hold the aircraft in a state of equilibrium, or trim. The stick force the pilot may need to apply to maintain equilibrium can be quite high, and all human beings find it impossible to maintain a constant stick force for more than a few seconds. Therefore, a means of reducing the stick force to zero is incorporated in all aircraft. This is known as trimming the aircraft. There are several devices used to trim an aircraft. The most common is the trim tab, which is the first trimming device we will look at. You can see the cockpit controls for trimming, plus the tailplane, the elevator, and the elevator trim tab. The trim tab is the small red aerofoil mounted on the trailing edge of the blue elevator. The majority of smaller aircraft have an exposed trim wheel in the cockpit. which the pilot can use to move the trim tab. The trim wheel works in a logical way. Move it down by its rear edge to trim the aircraft nose up, as you will see shortly. Some small aircraft and all modern jet transport aircraft have trim switches mounted on the control wheel. The trim switches also work in a logical way. Move them down to trim the aircraft nose up, again, as you will see shortly. All control movements in the following animations are exaggerated for clarity. Let's consider an aircraft with a forward CG, a nose-heavy aircraft. To maintain equilibrium, the pilot must move the stick aft to move the elevator up. Holding the elevator up requires a pull force. The aircraft is in equilibrium, in trim. To reduce the stick force to zero, the pilot must move the trim switches down, or move the rear edge of the trim wheel down. Making this trim input moves the trim tab down, away from neutral with the elevator. As the trim tab moves down, an aerodynamic upforce is generated on the elevator trim tab. Eventually, the moment from the trim tab becomes equal to the moment from the elevator. The stick force has been reduced to zero and the aircraft has been trimmed. Please note, when using a trim tab to trim an aircraft with a forward CG position, the cockpit control remains displaced aft from neutral. Your flight instructors will teach you to put and then hold the aircraft in the required attitude using the flying controls. Only after you have achieved equilibrium should you use the trimming devices to reduce the stick force to zero. To fly the aircraft using the trim to change the attitude is bad practice. Let us now have a look at one of the disadvantages of the trim tab: reduced aircraft nose-up pitch authority with a forward CG. Maximum elevator travel is limited by the primary stops. In this example, let's assume the elevator can move 30 degrees up from neutral and 30 degrees down from neutral, a total travel of 60 degrees. 60 degrees total elevator travel will always be available. Let's assume, once again, because of a forward CG, there is a requirement for the pilot to trim the aircraft nose up. You can see that there is reduced aircraft nose-up pitch authority from the elevator with an aircraft trimmed with a forward CG. This reduction in aircraft nose-up pitch authority might make it difficult for the pilot to flare the aircraft for landing. Some trim tabs are not adjustable in flight, but can be adjusted on the ground by maintenance personnel to correct a permanent out-of-trim condition. They are usually only fitted on the ailerons and rudder of light aircraft. When the early jet transport aircraft were being designed in the 1950s, it was found that an elevator trim tab did not provide enough pitch trim authority for the increased speed range and CG range required. So an alternative method of pitch trim had to be used: the variable incidence trimming tailplane. The variable incidence trimming tailplane is still in use on today's jet transport aircraft. You can see that the trim input controls in the cockpit are the same, but now pitch trim is accomplished by changing the incidence of the whole tailplane. As before, for pitch control, an elevator mounted on the trailing edge of the tailplane is still used. For pitch trim, the incidence of the tailplane is changed with the screw jack. The screw jack is mounted inside the rear fuselage and is driven by motors mounted on a gearbox at the base of the screw jack. Once again, we will consider an aircraft with a forward CG, a nose-heavy aircraft. As before, to maintain equilibrium, the pilot must move the stick aft to move the elevator up. Holding the elevator up requires a pull force. The aircraft is in equilibrium, in trim. To reduce the stick force to 0, the pilot must move the trim switches down. Making this trim input drives the screw jack, which in this case decreases the incidence of the tailplane. Please note that while the tailplane is trimming, the elevator is being returned to neutral. The decreased incidence of the tailplane has replaced the downforce from the elevator. The aircraft is still in equilibrium, but with 0 stick force. The aircraft has been trimmed. When the trim position is reached, the elevator is faired with the trimming tailplane. The cockpit pitch control has also been returned to its neutral position. Let's now have a look at the advantages of the variable incidence trimming tailplane over the trim tab. The first advantage is that compared to a trim tab, it is much more powerful and has the ability to trim for larger CG and speed ranges. However, there is a drawback associated with the increased power of the variable incidence trimming tailplane. If the tailplane were to change its incidence without being commanded, the pilot could not stop the aircraft from pitching out of control because the elevator is much smaller than the tailplane. This is known as stabilizer trim runaway, and safeguards have to be incorporated in the design to prevent it. Firstly, there is a mechanical brake inside the gearbox which engages and immobilizes the screw jack whenever a trim command from the flight deck is absent. This prevents the airflow from moving the stabilizer. Secondly, there are 2 switches on the control wheel in the cockpit. The switches are mounted side by side and are easily moved together by the pilot's thumb when required. The switches are wired in series so that if the contacts of one switch do not break the circuit when the pilot releases the switches, the other switch will break the circuit to stop the trim from running. There is also a warning light that illuminates to tell the pilots that the trim is running, and on the Boeing 737, which has exposed trim wheels, their clanking noise when rotating will be an unmistakable warning. If the stabilizer trim does run away, all inputs to the screw jack drive can be removed by emergency shut-off switch action on the flight deck. The second advantage of the variable incidence trimming tailplane is that there is less aerodynamic drag when the aircraft is in trim, a big advantage in the cruise. The third advantage is that trimming does not reduce the effective range of pitch control. As before, the total range of the elevator is limited by the primary stops. But because the elevator is faired with the tailplane when trimmed, both full-up elevator and full-down elevator from neutral is always available to the pilot for pitch control. The only disadvantage of the variable incidence trimming tailplane is that it is heavier than a trim tab and more complex. This disadvantage is far outweighed by its advantages. To maximize aerodynamic efficiency in the cruise, reducing the trim drag to an absolute minimum will significantly increase the distance that can be flown using a given amount of fuel. The illustration shows an aircraft in the cruise with the tailplane trim being used to generate the normal tail down force. As you know, lift must balance the aircraft weight plus any tail down force, so induced drag will be increased. Plus the tail down force is an aerodynamic force, which will further increase induced drag. These together make up the trim drag. We have seen that the variable incidence trimming tailplane gives less trim drag than the trim tab. Now we will consider the benefit from moving the aircraft CG in flight. In this case, we need to move the CG rearwards. This is done by pumping fuel from the wing tanks to a trim tank at the rear of the aeroplane, usually fitted inside the fin or the tailplane. Pumping the fuel to move the CG is an automatic function and in practice is a slow and almost continuous operation. But as usual, we have exaggerated the illustration for clarity. Please note that the trim switches are not being used, but the tailplane is changing incidence to maintain equilibrium as the fuel is being transferred from the wing to the tail, another automatic function. With power flying controls, there is no feedback of aerodynamic forces to the cockpit controls. The stick forces are generated by the artificial feel system. Therefore, when the aircraft is being trimmed, the trim system will have an input to the artificial feel system that reduces the stick forces as appropriate. We have now reached the end of our study of flying controls. Please feel free to review the lessons as many times as you like, because they contain a lot of detail in which the examiners are interested. In this series of lessons on flight mechanics, you'll be studying the forces acting on an aircraft in flight and the response of the aircraft to those forces. For an aircraft to be in steady, unaccelerated flight, the following conditions must exist. Forces acting downwards must exactly balance the forces acting upwards, and the forces acting backwards must exactly balance the forces acting forwards. In addition, the sum of all moments must be zero. When all these conditions are met, the aircraft is in a state of equilibrium. In straight and level flight, there are four forces acting on the aircraft: lift, weight, thrust, and drag. Weight acts through the centre of gravity, the CG, vertically downwards towards the centre of the Earth. Alternatively, weight can be said to act parallel to the force of gravity. Lift acts through the centre of pressure, CP, normal, or at 90 degrees, to the flight path. Drag acts backwards, parallel to the flight path. And thrust, for the purposes of this lesson, although not strictly true, can be said to act forwards, parallel to the flight path. For an aircraft to be in steady level flight, a condition of equilibrium must exist. This unaccelerated state of flight is achieved with the aircraft trimmed, with lift equal to weight, and the throttles set for thrust to equal drag. For steady level flight, then, the opposing forces must be equal. The proportion of the lift force to the drag force, known as the lift-drag ratio, for most modern aircraft is between 10 and 20 to 1. In simple terms, this means that lift is 10 to 20 times greater than drag. The lines of action of thrust and drag usually lie fairly close together, so the moment of this couple is small and will be disregarded for this study. The positions of the CG and CP are variable, but under normal circumstances will not be coincident. The CP will move forward as angle of attack increases, and will usually stay aft of the CG, unless the design allows the tailplane forces to stabilize the moments adequately with a forward CP. The CG will move as fuel is used, usually forward, but will usually, on conventional aircraft, remain in front of the CP. The function of the tailplane and elevator, or the stabilator, depending on the design, but referred to generally as the tailplane for simplicity, is to maintain equilibrium in pitch by supplying the force necessary to counter any moments resulting from CP and CG movement. With the CP providing a pitch down moment being behind the CG, the tail surfaces must provide a downforce. If the tailplane is producing a balancing force, this will add to or subtract from the lift required to balance the weight. For a downforce, the usual situation, lift must equal the weight plus the tailplane downforce, and for an upforce, lift must equal weight minus the tailplane upforce. For steady level flight at a constant weight, the lift force required will be constant, and at a steady speed, the wing will produce this lift at a given angle of attack. However, if the speed is changed, the angle of attack must change to maintain the same lift. As the lift changes with the square of the speed, but in direct proportion to the angle of attack, the angle required for constant lift will vary as shown on the graph on the screen. The minimum possible level flight speed, Vs, for any given lift force is achieved at the critical or stall angle of attack. For steady level flight at a constant speed, the thrust must equal the drag. Drag increases with speed above minimum drag speed, Vmd, and so to maintain a higher speed, the thrust must be increased by applying more power. To fly the speed at point A requires a thrust of T1, and to fly at speed B requires a thrust of T2. If the thrust is increased to T2 when the aircraft is at point A, the thrust will be greater than the drag, and the aircraft will accelerate in proportion to the excess thrust AC until it reaches point B, where the thrust and drag are again equal. If T2 is the maximum thrust available, then the speed at B will be the maximum speed achievable in level flight. In this second lesson on flight mechanics, we examine the relationship of the forces in a straight, steady climb. As in straight and level flight, the forces are lift, normal to the flight path, thrust and drag, parallel to it, and weight, parallel to the force of gravity. With the aircraft in a climb at an angle to the horizontal, the Greek letter gamma denoting the climb angle, the weight vector is inclined backwards relative to the flight path at the same angle as the climb flight path is to the horizontal. Note that the JAA objectives use the Greek theta instead of gamma for the climb angle. Weight, W, can be resolved into two components, one opposing lift with a value of W times cosine gamma, and the other acting in the same direction as drag with the value of W times sine gamma. This backwards component of weight, when added to the drag, creates a requirement for more thrust to re-establish equilibrium for steady flight. In a straight steady climb, lift is less than weight, because lift only has to support a proportion of the weight, with the proportion decreasing as climb angle increases. The remaining proportion of weight is supported by thrust. The ultimate illustration of this would be a vertical climb, where no lift is required, but lots of thrust is. You can see that, for a straight steady climb, the thrust required is greater than the drag, because the backward component of weight is added to the drag force. The ability of an aircraft to climb depends on the excess thrust available after opposing aerodynamic drag. The smaller the drag for a given thrust, the greater the ability to climb. For example, drag is less with flaps up, giving a larger climb angle or climb gradient. The climb angle achievable depends on excess thrust, thrust minus drag, and the weight. As both drag and thrust vary with IAS, the excess thrust will be greatest at one particular speed. This is the speed for the best angle of climb, known as Vx. This graph shows the variation of thrust with speed for a jet aircraft, where thrust is fairly constant with speed, and Vx is close to or coincident with Vmd. With a propeller-driven aircraft, where thrust decreases with speed, the maximum difference will usually occur at a speed below Vmd. The drag produced by an aircraft at a given IAS is not affected by altitude or temperature, but higher weights will increase drag, thus reducing the excess thrust available. Climb angle will therefore decrease with increasing weight. Increases in both altitude and temperature will cause a reduction in the thrust available from the engine or engines, which also reduces excess thrust. Climb angle will therefore reduce with increasing weight, altitude and temperature. In a descent, the disposition of the four forces, lift, weight, thrust and drag, will depend on how much power is used, but in all cases the lift vector is inclined forwards with the aircraft in a nose-down attitude. And the weight vector, as in the climb, can be split into two components. One, W cosine gamma, where gamma is the angle of descent, acts perpendicular to the flight path and is balanced by lift. And the other, W sine gamma, acts forward along the flight path and adds to the thrust, which is reduced for the descent. This added component restores the thrust-drag balance. If the nose of the aircraft is lowered with a constant thrust setting, the increased forward component of weight acting forward along the flight path will cause an increase in IAS. This increased IAS will result in a rise in drag, which will eventually balance the weight element, at which point equilibrium is restored and the speed will stabilize. If the throttles are closed, the thrust force is removed, and a larger forward component of weight is required to balance drag and maintain a constant IAS. This is achieved by lowering the nose of the aircraft to increase the descent angle, gamma. To sum up the arrangement of forces in a descent, lift is less than weight because lift only has to balance the component of weight perpendicular to the flight path, W cosine gamma. And thrust is less than drag because weight is giving a forward component in the same direction as thrust, W sine gamma. The total reaction of lift and drag opposes the weight vector. There may be emergency situations, typically a pressurization failure at high altitude, in which it is necessary for the aircraft to descend as quickly as possible. The high rate of descent necessary can be achieved by several means, which are usually used in combination according to the circumstances. The first action would normally be to close the throttles to minimize thrust and simultaneously lower the nose to initiate the descent. Drag can be increased by extending speed brakes or spoilers, and if the speed has to be kept low, say with structural failure or an unlatched door, the landing gear and possibly the flaps can be lowered as well, observing the appropriate limiting speeds. If there are no speed restrictions, the gear would be left up and the nose lowered to increase the speed up to the limiting IAS, VMO, or Mach number, MMO. If the initial limit is MMO, then IAS will be increasing as the aircraft descends, and at some stage the nose will have to be raised to keep the speed from exceeding VMO. The rates of descent achieved in an emergency descent can be quite high and would require a fair amount of anticipation by the pilot to level off at the required altitude. In a glide, that is, a descent without power, there is no thrust to provide the propulsive force and balance the drag. This is done by the component of weight acting along the flight path. In a glide, there are only three forces acting on the aircraft: lift, weight, and drag. The forward component of weight, W sine gamma, is a product of the descent angle gamma. The greater the descent angle, the greater will be the forward component of weight. This component must balance drag for the aircraft to be in a steady glide. It follows that, if drag is reduced and lift remains constant, the required balance of forces can be achieved at a smaller descent or glide angle. The angle of descent in the glide is a function only of the lift-drag ratio. The angle will be at its least when the lift-drag ratio is at its greatest, which is at the optimum angle of attack, which in turn corresponds to the minimum drag speed, VMD. It is important to remember that at speeds above or below VMD, the glide angle will be steeper. So, the maximum distance in a glide will be achieved when the aircraft is flown at its maximum lift-drag ratio at VMD. The maximum lift-drag ratio is independent of weight. Provided the aircraft is flown at its optimum angle of attack, the glide angle and the still air glide distance will be unchanged, whatever the weight. However, the speed corresponding to the optimum angle of attack, minimum drag speed, will change with weight. VMD increases as weight increases. A higher weight would give an increased forward component of weight, and the aircraft would accelerate towards the higher VMD, with lift increasing and drag increasing until it balances the higher weight component. Equilibrium is re-established at the same maximum lift-drag ratio, but at a higher IAS. At a higher weight, the aircraft will glide the same distance in still air, but at a higher speed, and consequently the rate of descent will be higher. The glide angle will determine the distance that the aircraft can glide for a given change of height. This distance would only be achieved in still air. If there is a wind, the ground speed will be affected, and so the distance will change. In a headwind, the ground distance will be reduced. And in a tailwind, the ground distance is increased. The maximum lift-drag ratio of an aircraft will only be obtained in the clean configuration. Extension of flaps, spoilers, speed brakes or landing gear will reduce the maximum lift-drag ratio and give a steeper glide angle, thus reducing glide range. The minimum rate of descent in the glide is obtained at the indicated airspeed, IAS, which requires minimum power, VMP. Flying at VMP in a glide will enable the aircraft to stay airborne as long as possible, but will not result in the shallowest glide angle or best glide range. As shown in the graph on the screen, VMP is a lower IAS than VMD. Wind speed and direction have no effect on the rate of descent. One way of portraying the relationship of VMP and VMD is shown in the diagram on the screen, which is known as the whole aeroplane CL/CD polar curve. This lesson concludes the topic of descending. The next lesson continues with the flight mechanics of turning. This lesson on the mechanics of flight deals with the forces and factors involved in flying a level, balanced turn. For an aircraft to change direction, it requires a force that will deflect it effectively towards the centre of the arc around which it will fly. This force is called the centripetal force, that is, centre-seeking. As you can see from the diagram, with the aircraft banked, the lift vector is also tilted, and it is the horizontal component of lift which causes the aircraft to turn by providing the centripetal force. If the aircraft is banked and the angle of attack is maintained at the same value as in straight flight, the vertical component of lift would be insufficient to balance the weight, and the aircraft would descend. As the angle of bank increases, the angle of attack must be increased to achieve a greater total lift, with the vertical component being large enough to balance the weight and maintain level flight, and the horizontal component providing the centripetal force. In a steady level turn, if thrust is ignored, lift provides the force to balance weight and the centripetal force to turn the aircraft. If two different aircraft can fly at the same TAS and angle of bank, their radius of turn will be the same, since radius of turn is independent of weight or aircraft type. However, not all aircraft can reach the same angle of bank at the same TAS. With a heavier aircraft, the vertical component of lift required increases, but the centripetal force necessary to maintain the same radius of turn also increases in the same proportion. The lift required, although greater, has the same inclination to the vertical as before, and the bank angle is the same. Rate 1 is 180 degrees per minute, or 3 degrees per second, and rate 2 is double that, at 360 degrees per minute, or 6 degrees per second. Rate 1 is the standard turn rate for instrument flight rules. A useful rule of thumb for calculating the angle of bank required to achieve a rate 1 turn is true airspeed over 10 plus 7. For example, at 150 knots TAS, the bank required is 22 degrees. As you have already seen, in a bank turn, the lift must be increased to provide not only centripetal force from the horizontal component, but also a vertical component sufficient to balance the weight. As bank is increased, the total lift required, and thus the load factor as well, must increase to maintain the vertical component's value for a level turn. The load factor, or G in common parlance, is the relationship between total lift and weight, can be expressed in the equation load factor N equals lift over weight, which equals 1 over cosine phi, which equals second phi. The trigonometry of this is fully explained in the lesson on stalling. The relationship can also be shown graphically, and the chart is valid for any aircraft. It can be seen that the curve is exponential, that is, the G increases at an increasing rate with angle of bank. The point to remember is that in a level turn, load factor is a function only of bank angle. Constant bank, constant G. There are certain limitations which can restrict the performance of an aircraft in the turn. For each aircraft type, there is a design limit load factor. For modern high-speed jet transports, the limit is 2.5 G. From the graph, it can be seen that this occurs at 67 degrees of bank, which will determine a turn radius dependent on the TAS. This will be the minimum radius possible without exceeding the G limit. If speed is kept constant but bank is increased, the angle of attack must be increased to provide the further extra lift required. At the stalling or critical angle, no further increase in bank or decrease in radius is possible. Since stalling speed varies with weight and G, this limit will be a function of those two factors. The extra lift required during a turn will result in greater induced drag, so to maintain the straight flight speed, more thrust is required. As more bank is applied, more thrust is needed, and eventually maximum thrust will be reached. At this point, it is not possible to increase the bank or decrease radius. Whether this thrust limit or the maximum load factor is reached first will depend on the G limit and the thrust available. If the thrust available is adequate, the minimum radius of turn occurs at the intersection of the stall limit and the strength or load limit. The speed at this point is VA, the maximum maneuvering speed. The heavier the aircraft, the greater will be the minimum radius of turn. There are several factors which can cause uncoordinated flight. Adverse aileron yaw, engine torque, gyroscopic precession, and spiral slipstream from the propeller, and asymmetric flight, plus, of course, unbalanced control movements by the pilot. Uncoordinated flight exists when the aircraft is side-slipping, and indication to the pilot of side-slip is given by the inclinometer portion, the ball, of the turn coordinator. The miniature aeroplane indicates rate and direction of turn, but not angle of bank. The level index shows when the aircraft is not turning, but not necessarily when the wings are level. When the miniature aeroplane's wingtip is against either of the rate 1 indices, the aircraft is turning at rate 1 or 3 degrees a second. A reminder of rate 1 is below the ball, 2 min referring to the fact that a full 360-degree turn at rate 1 takes 2 minutes. The inclinometer, as already mentioned, shows the pilot if his turn is balanced. Coordinated or balanced flight is maintained by keeping the ball centered between the reference lines with the rudder. If the ball is out to one side, rudder pressure should be applied in that direction. Stepping on the ball is a useful way to remember which way to push on the rudder pedals. Side-slipping towards the center of the turn moves the ball to the inside of the turn, and vice versa. Changing the angle of bank can also restore balanced flight, but will alter the rate of turn. The second instrument here shows an uncoordinated turn to the right, with the aircraft side-slipping towards the center of the turn, a slipping turn. Right rudder or less bank would balance the turn. The third instrument also shows an uncoordinated turn to the right, with the aircraft side-slipping towards the outside of the turn, a skidding turn. Left rudder or more bank would balance the turn. This concludes the lessons on turning flight mechanics. The flight mechanics series of lessons concludes with the next lesson on asymmetric flight.
When an engine fails on a multi-engine aircraft, there will be a decrease in thrust, and on propeller-driven aircraft, an increase in drag on the side with the failed engine. The results will be that the airspeed will decay, the nose will drop, but most significantly, the aircraft will yaw immediately towards the failed or dead engine. Controlling that yaw is of vital importance. The yawing moment is the product of thrust from the operating engine multiplied by the distance between the thrust line and the center of gravity, the thrust arm, plus any drag from the failed engine multiplied by the distance between the engine centerline and the CG. The strength of the yawing moment will depend on 3 factors: how much thrust the engine is developing, depending on throttle setting and density altitude, the distance between the thrust line and the CG, the thrust arm, and the drag from the failed engine. If rudder is applied to counter the yaw, it will generate a moment which is the product of the rudder force multiplied by the distance between the rudder center of pressure and the CG. At this initial stage, the pilot's ability to counteract the asymmetric yawing moment will depend on the rudder displacement, which affects the rudder force, the IAS, also affecting the rudder force, and the CG position, affecting the rudder arm. Under a certain combination of conditions, control difficulties can arise under asymmetric thrust. Let us assume that the live engine is at a high thrust setting, the rudder is at its full deflection, and the CG is at its rearmost limit, that is, giving the shortest rudder arm. If the IAS, the dynamic pressure, is just sufficient to produce enough rudder moment to counter the yawing moment, there will be no yaw. However, any decrease in the IAS will reduce the rudder force, and the aircraft will yaw uncontrollably towards the dead engine. This uncontrollable yaw, in this case to the left, will cause the aircraft to roll uncontrollably, also to the left, owing to the greater lift on the starboard wing whilst yawing left. The aircraft will enter a spiral dive to the left, which at the low speed would be impossible to stop with flight controls alone. If this were to happen close to the ground, the result would be disastrous. In these extreme circumstances, the only way to regain control would be to minimize thrust on the live engine or engines, to remove the yawing moment and permit a controlled forced landing. Thus, there is a minimum IAS at which directional control can be maintained under a given set of conditions after engine failure in a multi-engine aircraft. This minimum speed, which will vary with temperature and density, is called VMC, minimum control speed. There are different speeds for ground and air engine failures, and for different configurations. These are described fully in due course. One of the factors influencing the yawing moment following engine failure in a multi-engine aircraft is the length of the thrust arm. That is, the distance from the CG to the thrust line of the operating engine. In the case of a prop-driven aircraft, the length of the thrust arm is determined by the asymmetric blade effect of the propeller. At positive angles of attack, the thrust line of a propeller rotating clockwise when viewed from the rear is displaced to the right. This is because the downgoing blade generates more thrust than the upgoing blade. This phenomenon is fully explained in the lesson on propellers. If both propellers rotate clockwise, the right or starboard engine's thrust arm will be longer than that of the port engine. So, if the left engine fails, the thrust of the right engine acts through a longer thrust arm and generates a bigger yawing moment, and a higher IAS would be necessary to maintain directional control than if the right engine failed. Thus, at a given IAS, the given situation would be more critical if the left engine failed. The critical engine, then, is the one that would give rise to the biggest yawing moment if it were to fail. To overcome the disadvantage of having a critical engine on smaller twins, their propellers may be geared to rotate in opposite directions, or counter-rotate, with the downgoing blades inboard, giving both engines the shortest possible thrust arm. Bigger turboprop aircraft, such as the King Air and larger, will have co-rotating propellers, turning in the same direction. In the case of four-engine jets, either outboard will be a critical engine. Although the moments are balanced in the diagram on screen, the forces are not. The unbalanced side force from the rudder can be balanced in two ways, either with the wings level or by banking towards the live engine, which in a marginal situation is the preferred method, as will be explained shortly. In the wings level method, rudder is used to prevent yaw, and the ailerons are used to keep the wings level. Yawing towards the live engine gives a side-slip force on the keel surfaces behind the CG opposite to the rudder. The turn indicator will be neutral, and the ball central. This paradox of asymmetric thrust, where the aircraft is side-slipping but the ball is in the middle, is the exception to the rule of balanced coordinated flight. The advantage of the wings level method of balancing the forces is the strong horizontal visual and instrument reference available to the pilot. The disadvantages are that extra parasite drag from the side slip will reduce climb performance, which would be vital when close to the ground, and that there is a possibility of fin stall if the side slip angle is excessive, which would worsen directional control problems considerably. It is more aerodynamically efficient to balance the rudder side force by banking towards the live engine, so that lift gives a lateral component to oppose the rudder force. The bank angle must be restricted to 5 degrees to prevent significant reduction of the vertical lift component. Banking towards the live engine also reduces the side force on the fin from side slip, which effectively reduces the yawing moment and gives more rudder authority to stop the yaw. The cockpit indications on the turn coordinator will be no turn, but the ball will be out to the right. This is the corollary of the indication in the wings level method, there being no side slip, but the ball is not central. The advantage of this method is its better aerodynamic efficiency, without the side slip drag penalty, making it better for use in marginal situations. But it is more difficult than the wings level method for the pilot to fly consistently. In practice, however, pilots will tend to use the wings level method initially, with its simpler handling references, usually combining the techniques only under marginal conditions, when the better aerodynamic efficiency of bank to the live engine or engines is of greater importance. The rolling and yawing moments, and the power of the flight controls to balance them, will determine the controllability of an aircraft with asymmetric thrust. These rolling and yawing moments are affected by thrust on the live engine. Yawing moment increases with thrust, and the further out the engine is mounted on the wing, the larger the moment. Thrust is greatest at low speed and maximum power. Thrust reduces with increases in altitude and temperature, that is, higher density altitudes. The worst case for an engine failure is thus after takeoff at sea level on a cold day. The drag from the propeller itself will depend on whether it is stationary, windmilling, or feathered, but there will always be some contribution to the yawing moment. If the propeller is stationary, it is generating some drag from the blades, which could be at a relatively large angle to the airflow, but no torque. A windmilling propeller will produce a large amount of drag, being driven by the relative airflow, generating both drag and torque. The propeller will also have the load of turning the dead engine, unless an automatic decoupling device is fitted. A feathered propeller will cause the least possible drag. There is no torque, since it is not rotating, and the parasite drag is at a minimum with the blade's edge onto the airflow. If both engines rotate clockwise, the right engine has a longer thrust arm, and failure of the left engine gives a greater yaw moment. This asymmetric blade effect, or P factor, is absent with counter-rotating and contra-rotating propellers, and of course on jets. The aircraft rotates around its CG, but its fore and aft position has no effect on the yawing moment from a failed engine. The rudder arm is affected, however, with an aft CG giving the worst case with the least rudder effectiveness. When the engine turns the propeller, the equal and opposite reaction tries to turn the engine the other way, the torque effect being to roll the aircraft to the left. If the left engine were to fail, it would result in a bigger rolling moment to the left. As with asymmetric blade effect, this happens only with co-rotating propellers. Note, however, that if the propeller is windmilling, the torque is reversed, but is much less than the torque of the live engine. Any propeller-driven multi-engine aircraft will suffer a loss of lift from the slipstream-induced faster airflow over the wing behind the failed engine. The reduction in total lift will give a tendency to descend, but more importantly, a roll towards the failed engine. The roll is exacerbated if flaps located behind the failed engine and its counterpart on the live side are down, owing to the higher CL. If the aircraft is being flown wings level asymmetric, it will be side-slipping, and the dihedral of the forward wing, in this case the port or left wing, will generate more lift, compensating in part for the loss of lift from the slipstream. Any weight increase will require a higher angle of attack at any given speed. This will have the result of increasing asymmetric blade effect with a bigger yawing moment, and partially masking the fin and rudder, making them less effective. Ultimately, the most important element in the control of the aircraft under asymmetric conditions is dynamic pressure, which is a measure of the calibrated airspeed, CAS, which is, in turn, indicated airspeed, IAS, corrected for position error. IAS, of course, is what the pilot sees on his airspeed indicator. Higher IAS means more control effectiveness, and consequently greater rudder movement, all other parameters being unchanged. We can summarize the factors affecting the roll and yaw moments when on asymmetric thrust as follows: thrust on the live engine, altitude, drag from the dead engine and propeller, asymmetric blade effect, center of gravity position, torque reaction, difference in lift from slipstream, rolling moment due to side slip, weight, and finally the vital element of IAS, which determines the amount of control the pilot has over the aircraft. You have learned that when a multi-engine aircraft suffers an engine failure, there are several variables which affect both the yawing moment and the rudder moment used to oppose it. You have also learned that there is a minimum IAS, VMC, below which it is impossible to maintain directional control under asymmetric thrust. Airworthiness authorities, the one quoted in this lesson being the JAA, have laid down conditions to be satisfied in establishing the minimum airspeeds for inclusion in the flight manual of a new type. In most instances, the conditions are based on a worst case. A safety factor is built into these speeds to allow for aircraft age and the response time of an average pilot. Because there are distinct variations in an aircraft's handling characteristics in certain configurations and stages of flight, minimum control speed, VMC, has three separate specifications, which are VMCA, the minimum control speed in the air, VMCG, the minimum control speed on the ground, and VMCL, the minimum control speed in the landing configuration. For aircraft with 3 or more engines, airborne speeds will also be defined for single and double engine failures, nominated VMCA1 and VMCA2, and so on. The JAA and its successor, EASA, specify the parameters for determining VMCA. Here we have paraphrased the JAA requirements as laid down in Regulation JAR 25.149. VMCA is the calibrated airspeed at which, when the critical engine is suddenly made inoperative, it is possible to maintain control of the aeroplane with that engine still inoperative and maintain straight flight with an angle of bank of not more than 5 degrees. VMCA may not exceed 1.13 times the reference stall speed under these conditions. Maximum available takeoff power or thrust on the engines, the aeroplane trimmed for takeoff, the most unfavourable centre of gravity position, maximum sea level takeoff weight, the aeroplane in its most critical takeoff configuration, but with gear up, the aeroplane airborne and the ground effect negligible, and, if applicable, the propeller of the inoperative engine either windmilling or, if an automatic feathering device is fitted, feathered. The rudder control forces required to maintain control at VMCA may not exceed 150 pounds, nor may it be necessary to reduce power or thrust on the operative engines. It should be noted that no performance requirements are specified. The only necessity is directional control. There are several factors that affect VMCA. They are as follows. Banking towards the live engine reduces the rudder deflection required, and so allows a lower VMCA. 5 degrees is stipulated because larger bank angles would significantly diminish the vertical component of lift, requiring a higher angle of attack with its attendant drag penalty. The position of the CG, around which the aircraft rotates, will directly affect the length of the rudder arm, and thus the power of the fin and rudder to give directional control and stability. The worst case is with the shortest arm, the CG being at its aft limit. As well as the rudder, the aileron's effectiveness is reduced at lower airspeeds, requiring greater deflection to keep the wings level or hold the required bank under asymmetric power. If the down aileron deflection is large at low speed, it may be enough to cause a stall of that wing, giving an uncontrollable roll towards the dead engine. VMCA must be high enough to avoid this situation. Flap position affects the lift-drag ratio, nose-down pitching moment and stalling speed. With asymmetric thrust, flap reduces climb rate whilst increasing the margin above the stall, but does not directly affect VMCA. However, if takeoff flap is used, there will be a greater difference of slipstream-associated lift between wings, giving a larger rolling moment, needing more aileron, and indirectly increasing VMCA. The undercarriage increases drag and reduces performance. The extra keel surface in front of the CG slightly reduces directional stability, opposing the fin and rudder, with a small increase in VMCA. Increases in altitude and temperature will reduce the thrust from the live engine or engines unless boosted, and VMCA will be reduced accordingly. The relationship between stalling speed and VMCA can be seen on the graph on screen, in which the VMCA curve intersects with VS, typically around 3,000 feet. Thus, above this altitude, an aircraft would reach the stall before VMCA on deceleration after engine failure. This gives a smaller speed margin above loss of control. JAR regulation CS 25.149 gives the parameters for ground minimum control speed. It states that VMCG is the calibrated airspeed during the takeoff run at which, when the critical engine is suddenly made inoperative, it is possible to maintain control of the aeroplane with the use of primary aerodynamic controls alone, that is, without the use of nosewheel steering, to enable takeoff to be safely continued using normal piloting skill. The rudder force may not exceed 150 pounds or 68.1 kilos, and until the aircraft becomes airborne, the lateral control may only be used to the extent of keeping the wings level. In the determination of VMCG, assuming that the path of the aeroplane accelerating with all engines operating is along the centre of the runway, its path from the point at which the critical engine is made inoperative to the point at which recovery to a direction parallel to the centreline is completed may not deviate more than 30 feet or 9.144 metres laterally from the centreline at any point. As with VMCA, these conditions must be established with maximum available takeoff power or thrust on the engines, the aeroplane trimmed for takeoff, the most unfavourable CG position, and maximum sea level takeoff weight. There are several factors that affect VMCG. They are as follows. As with VMCA, increases in altitude and temperature will reduce the thrust produced by the live engine or engines if unsupercharged, and VMCG will be reduced accordingly. Nose wheel steering is designed for taxiing, making tight turns at low speed, turning off the runway, parking, and so on. When taking off on wet, icy or slippery runways, the nose wheel can lose adhesion and have little steering effect. VMCG is established during flight testing, usually on a dry runway. If the test pilot were to use the steering, it will give a false low control speed, which could result in loss of control if used in emergencies. The regulations are established according to worst-case parameters to give the maximum safety factor. The rudder arm, when the aircraft is on the ground, is shorter than when airborne, as it rotates around the main undercarriage, which is aft of the CG. On most aircraft, therefore, VMCG will be higher than VMCA. JAR regulation CS 25.149 gives the parameters for landing minimum control speed, VMCL. VMCL is the calibrated airspeed at which, when the critical engine is suddenly made inoperative, it is possible to maintain control with that engine inoperative and maintain straight flight with no more than 5 degrees of bank. The airspeed must be established with the aeroplane in the most critical configuration for approach and landing, with all engines operating, the most unfavourable CG, the aeroplane trimmed for approach with all engines operating, the most unfavourable weight. For propeller aeroplanes, the propeller of the inoperative engine in the position it achieves without pilot action, and go-around power or thrust setting on the operating engine or engines. In demonstrating VMCL, the rudder force may not exceed 150 pounds. The aeroplane may not exhibit hazardous flight characteristics or require exceptional piloting skill, alertness or strength, and lateral control must be sufficient to roll the aeroplane from an initial condition of steady flight through an angle of 20 degrees in the direction necessary to turn away from the inoperative engine or engines in not more than 5 seconds. At low air speeds, and therefore low dynamic pressures, the effectiveness of all flying controls for a given displacement is reduced. This effect on the rudder has already been mentioned, but the ailerons are similarly affected, of course. To obtain the required response, greater deflection must be used at low speed. The downgoing aileron will add to the yawing moment from increased induced drag, and may even stall the outer section of the wing at low IASs. Adequate aileron effectiveness is clearly very important, since VMCL requirements include rolling and not just directional control. JAA's document CS 25.149 sets out the criteria for establishing the various minimum control speeds for the certification of a new aircraft type. Once established, the speeds will be included in the aircraft's flight manual. From the extracts that have been detailed in this lesson, we can summarize several significant points. First, regarding VMCG, nose wheel steering may not be used when establishing the speed, since its use would artificially reduce VMCG, and on a slippery runway, nose wheel steering is likely to be ineffective at speeds well above taxiing speed, so would not be able to control the aircraft directionally at or above the stated VMCG. For VMCL, the criteria include a roll requirement, and not just one for directional control, as with the other VMC categories. As a general point, the thrust developed by an engine depends on air density, so thrust will decrease with increasing altitude and temperature. The yawing moment due to asymmetric thrust will thus reduce with altitude and temperature, enabling control to be maintained at a lower IAS. VMC therefore decreases with higher density altitude. You learned in the earlier flight mechanics lesson on climbing that an aircraft's ability to climb depends on the excess thrust available after aerodynamic drag is balanced. If a twin-engine aircraft loses an engine, thrust is reduced by 50%. But excess thrust, that is, thrust minus aerodynamic drag, is reduced by more than 50%, as shown in the graph on the screen. The ability to climb may be reduced by as much as 80%. The angle of climb is determined by the excess thrust available, and will be a maximum when the aircraft is flown at the speed where excess thrust is at a maximum. In other words, at a maximum thrust-drag ratio. Since thrust decreases with forward speed, and total drag increases above and below the minimum drag speed, VIMD, the best angle of climb is achieved at a speed below VIMD, but at a safe margin above the stall speed. The IAS for best angle of climb is Vx for all engines operating, and on twin-engine aircraft, Vxse is best for single-engine climb angle. Rate of climb is determined by the excess power available. Power is the rate of doing work, that is, thrust or drag times true airspeed, thrust and drag being forces, and TAS being the only real speed. Although thrust reduces with speed, total power available increases to a point because of the speed factor. Similarly, power required is a measure of drag times TAS. So excess power available determines the available rate of climb. The airspeed for best rate of climb is Vy for all engines operating, and Vyse for best single engine rate of climb. Vy and Vyse are higher than Vx and Vxse, and provide a safer margin above both stall and VMCA. Under most circumstances, Vy and Vyse are the best speeds to use. On small twin-engine aircraft, Vyse is marked on the airspeed indicator by a blue radial line, and is referred to as blue line speed. Considering all the foregoing factors, we can conclude that at a given altitude, airspeed and power setting, excess thrust depends on the amount of drag being generated, and this in turn will depend on configuration, weight, and whether turns are required. The control surface deflections required to balance asymmetric thrust will also cause drag. It is essential, therefore, that after an engine failure, particularly during takeoff or go-around, drag is reduced and no turns are made until safely clear of the ground. Drag can be reduced by feathering the propeller of the failed engine, raising the landing gear, raising the flaps at a safe height and speed, closing the cowl flaps on the dead engine if fitted, and applying 5 degrees of bank towards the live engine. Flying at blue line speed, Vyse, with maximum permissible thrust on the live engine, will provide maximum performance and optimum control of the aeroplane. While studying principles of flight, for simplicity, we assume that air is incompressible, but this is only valid for low-speed flight. For high-speed flight, we must consider changes in air density due to the changes in air pressure. This is known as compressible flow. When an aircraft moves through the air, pressure waves are generated. To generate some pressure waves, we're going to hit the nose of a stationary aircraft with a hammer, but in flight it will be particles of air that generate the pressure waves. The vibrations from the blow generate a series of pressure waves that move outwards through the air from where the hammer hit the aircraft, the point source. If we zoom out a bit, we can see what is going on more clearly, and for clarity, we'll show just one pressure wave. The pressure wave propagated from its point source, and then the picture was frozen. In the time between the pressure wave being generated and freezing the picture, the pressure wave moved through the air at a certain speed. The speed of pressure wave propagation is called the local speed of sound, represented by lowercase a. The only thing that will affect the speed of sound is the outside air temperature. The higher the temperature, the higher the speed of sound. In the same time interval, but with a higher temperature, the pressure wave would have propagated further, but not so far at a lower temperature. At a constant outside air temperature, do you think the pressure wave will look the same if the aircraft is moving when the pressure wave is generated? Of course it will. Nothing has changed. The pressure wave was generated in the same place, and the air temperature was the same. So the pressure wave will travel the same distance through the air in the same time. But in the time it took for the pressure wave to propagate, the aircraft will have moved forward from the point source of the pressure wave. The pressure wave moved through the air at the local speed of sound, and the aircraft moved through the air at its true airspeed. To understand the relationship between the local speed of sound and the aircraft true airspeed, we need to remind ourselves of a fixed reference point, the relative airflow. True airspeed is the speed of the aircraft through the air. But which air? The air just in front of the leading pressure wave. The trailing pressure wave is included for reference purposes only. During the study of high-speed flight, the most important aspect of the relative airflow is that it is close to, but as yet unaffected by, the presence of the aircraft. For general review, the relative airflow is also parallel to, and in the opposite direction to, the aircraft flight path, and the length of the vector represents the true airspeed of the aircraft. As soon as the pressure wave passes over an air particle, it is no longer relative airflow. It becomes effective airflow. More about this in a minute. Throughout our study of high-speed flight, there are two major characteristics in which we are interested. The one we will illustrate now is the proximity of the aircraft to the leading pressure wave. The second characteristic is the formation of shock waves, which we will look at later. There is a ratio between the aircraft true airspeed and the local speed of sound. This ratio is called the Mach number, usually shortened to m. The true airspeed of the aircraft in this illustration is 264 knots, and the local speed of sound is 660 knots at 15 degrees C. The Mach number is therefore 0.4. This is said as Mach 0.4. It is important to remember that both the speed of the aircraft and the speed of the pressure wave use the relative airflow as the reference air through which they are moving. We learned earlier that relative airflow can also be called free stream flow. So the Mach number we are discussing here is called the free stream Mach number. The free stream Mach number is basically what is presented on the aircraft Mach meter. The scale shows the aircraft at 4/10 the distance from the point source to the leading pressure wave. But this fact doesn't help us understand how high-speed flight affects the aircraft. It is this that will have an effect on the aircraft: how close the aircraft is to the leading pressure wave. We can now examine how the pressure wave changes the airflow approaching the aircraft. As soon as the pressure wave passes over an air particle, it is no longer relative airflow. It becomes effective airflow. The leading pressure wave effectively acts as a messenger. It tells the air, "Here comes an aeroplane, you'd better get out of the way." You can see that as soon as the pressure wave passes over the air, it starts to upwash. The higher the Mach number, the closer the aircraft is to the leading pressure wave, and consequently, the air has to upwash through a greater angle. You learned during your study of stalling that this will cause CLmax to decrease. Hence, stall speed will increase. The effect of this change will be discussed in detail later. Anything that is moving will have a Mach number. A person walking will be travelling at Mach 0.005, firmly in the low-speed flight region, where we don't need to worry about how close we are to the leading pressure wave. A training plane cruises at about Mach 0.14. A light twin at Mach 0.3. And a turboprop commuter aircraft at Mach 0.4. All these examples operate at speeds less than Mach 0.4, when their proximity to the leading pressure wave has no significance. It is only aircraft that operate above Mach 0.4 that need to know their proximity to the leading pressure wave, and consequently will be fitted with a Mach meter to tell the flight crew the aircraft Mach number. We'll now consider something called the critical Mach number. The critical Mach number is not used operationally, but is an important reference for your understanding of high-speed flight and your ability to answer exam questions. Here is a view of the wing, with the airflow accelerating over the top surface. The airflow will reach maximum velocity relative to the wing surface at the point of minimum cross-sectional area of the airflow. The maximum velocity of air on the wing will always be faster than the true airspeed. Otherwise, there would be no lift generated. The maximum velocity of air on the wing is called local velocity, because we are discussing air relative to the aeroplane surface. We can now introduce a Mach number called the local Mach number. The local Mach number is the ratio between the speed of the local velocity over the surface and the local speed of sound. Remember, the local Mach number will always be higher than the free stream Mach number. In this example, the free stream Mach number is Mach 0.55, and the local Mach number is higher at Mach 0.8. Let's see what happens as the aircraft accelerates in level flight. Both the free stream Mach number and the local Mach number are increasing. Notice the local Mach number has now reached the same value as the speed of sound, Mach 1. Bear in mind that the free stream Mach number is effectively the aircraft Mach number you'll be seeing on your Mach meter. The aircraft Mach number, at which the local velocity first reaches Mach 1, is called the critical Mach number. The critical Mach number is usually shortened to m-crit. The reason that m-crit is such an important reference is that as soon as m-crit is exceeded by even the smallest margin, a shock wave will start to form at the point of maximum local velocity. In the next lesson, we will examine why shock waves form, and later we'll look at their effect on the operation of aircraft during high-speed flight.